In this vignette, we will be discussing missing data, specifically different types of missing data, the impact missing data can have on our analysis, and some ways to deal with that missingness. So missing data completely at random is the first and best scenario. That is, no factors relating to the samples, measured or not measured, influenced which observations have missing data. Missing at random is very different from missing completely at random. Here, some important factors may have influenced which data are missing, but the probability of missingness is a function of variables that were measured. So we may not have measured the primary cause of missingness, but we've captured the information that caused them to be missing. We have enough correlated variables that we can, we've captured that information. Then we have informative missing data. Now these are biased in some way by other confounding variables. This results in estimates that are higher or lower than they should be, and it's often nearly impossible to detect without some outside information, like experience with past studies or an intimate knowledge of the population under study. So some examples of these include a study that ends prematurely, and some data are not able to be collected independent of any sample characteristics. This would be considered missing completely at random. The only thing that caused the missingness in this example is that the study ended early. So unless you have changed how you're sampling observations, there should be nothing different about observations that were followed as long as they were supposed to be. Another example would be individuals with depression being more likely to be lost to follow-up, resulting in missing data. As long as the loss to follow-up isn't related to the variable that's missing, like the number of cigarettes smoked each week during a study, we can assume that the number of cigarettes smoked by the individuals we did observe is representative of the number of cigarettes smoked by individuals we didn't observe. This is an example of missing at random. There are factors, measured or not, that are causing some missingness in some observations and not others. But we're able to capture that, and it should affect both cases and controls the same. Another example is that some unmeasured confounding variable like location, perhaps the country that we're sampling from has systemic poverty. This location influences heavy smokers in the treatment group to drop out of the study at a higher rate than individuals from more affluent region who tend to smoke less. This could cause all sorts of problems in our analysis, and biases could creep in. Fortunately, in this example, there are things that we can do with our study design that will ameliorate this effect. The first thing would be to ensure that if we know we're going to be sampling from regions with very different socioeconomic status, we want to be sure that the background of our cases and controls is as similar as possible. So we could match the cases and controls by socioeconomic status, age, gender. Doing this will condition out those potential biases. Now, if we're only missing a few data points in a large data set, you probably don't need to worry so much about missingness. But if you have a data set with a lot of missingness, you should be very careful how you approach the data analysis. Ask yourself, what is the rate of missingness in each group? Are there any subgroups that have higher rates of missingness? Is there anything we didn't measure that could be influencing the high rate of missingness? Are there any factors in our disease model that would cause an individual to have missing data? This is something that you should actually think about when you're designing your study. If the answer to your question is yes, then you had a lot of missingness, your analysis might be doomed if you haven't already compensated for it somehow in your study design. Also, what other relationships between observed data and missingness exist? Are there any other factors that you know of that might be affecting missingness? Again, if you're unaware of a factor that's biasing your study, you may not be able to detect it after your data have been collected. You might guess that a particular factor has influenced missingness, but unless you've collected that information, you probably won't ever know for sure. Unless you go back and collect more data, which can cost lots of time and money. So informative missingness can cause unexpected problems, including false associations. For example, in the 2016 presidential election, opinion polls predicting the outcome were dead wrong. One of the most likely causes of this is because of undecided voters, that is, likely voters with missing data. These voters, it seems, voted disproportionately for President Trump, violating our assumption that undecided voters were similar to the average American. This wasn't the case. By average American, I mean those that had responded, that didn't have missing data. So the average measured sample in our data set, that's probably a better way to say it. This wasn't a case of pollsters wishing to influence the electorate or some act of neglect on their part. Rather, it appears that those who were undecided up to the last minute were far more likely to vote for Trump than expected. This failed assumption is probably what resulted in unreliable polling leading up to the election. In other words, incorrect predictions were probably due to informative missingness in the polling data. So here we are going to generate a data set with a lot of missing data. We have a system where y is a function of continuous variables x1 and x2, and this categorical variable g. We're going to use the prod_na function from the MissForest package to generate 10% missingness in our data. Here we set the percent of missingness at 10%. And this is without respect to anything, so this is missing completely at random. When we look at a summary of our data frame, we see that about 10% missingness across the board. Because of how missingness is generated, again, this is a case of missing completely at random. And we've removed data without regard to any factors associated to our outcome variable y. So here we have the number of missing values for each of the variables in our data set. Now, the easiest way to deal with missing data is to just ignore it. In this case, we have sufficient data to observe statistical significance. None of our confidence intervals crosses 0 except for the intercept, which we would expect to. But as we look at the following examples, pay attention how the estimates and confidence intervals change. According to the model we used to generate y, the true population estimates for all of these coefficients are equal to 1, except the intercept, that is, which should be 0. So all of these estimates should be 1. This should be close to 0 if it were exactly like what we expect. Obviously, when we take a sample, things are going to be a little bit different each time we run it. When we ignore missingness in this data set, we end up throwing about 30% of the data out. Because while only 10% of the data are missing, 30% of the observations, that is 30% of the rows, have at least one variable missing. That's going to affect how well we can estimate these effects. We didn't do too badly here, but could we perhaps do better? Another way that we can capture some of our lost data back is by replacing missing values with the group mean. These mean values will have at most a minimal effect on the estimated coefficients. but it will allow us to include observations that otherwise would have been dropped from the analysis. The non-missing data from these observations can then be included in the model. Remember that while only 10% of the values in our data set are missing, we need to drop 30% of our observations because they have one or more missing values. So this first row of our data set, for example, right here, it only has one missing value, but because of this missing value for G, this entire row of that data would need to be thrown out if we were using the simple strategy of just ignoring it. However, when we replace it with the mean of all the observed values for G, which is about 0.48, is what we observe, then we are able to include the rest of the observations, x1, x2, and y, in our model. This mean value of G won't change the model in any noticeable way, but it will result in a net addition of information. So here we're replacing any missing values with the observed mean. And we can see here that the estimates are a little bit closer to 1, which is what we would expect from the population we sampled from. Because our effective sample size is bigger, we also have a slightly better chance to observe statistical significance than we would otherwise. So here we are, if it's missing, we're going to replace it with the mean of all the other observations. Otherwise, we just keep the value that we have. And then again, when we run this linear model, we are piping the results to the CI function from the from the gmodels package, and we're only keeping the first 3 columns of the data of the output, the estimate, lower and upper bounds. So a better way to estimate values for our missing data is to use imputation. This uses a statistical model to replace the missing value with the most plausible estimate after taking the observed values into account. For example, if we're looking at the association between height and weight for children on different diets, we would probably want to take age, gender, and other relevant data into account when estimating the value for height if it were missing. We could use the overall mean of height of all the children in the study as an estimate for an 11-year-old girl, but it would make a lot more sense to use the height of other 11-year-old girls as the estimate rather than including 15-year-old boys in that estimate. We'll use the Miss Forrest function from the Miss Forrest package to do the imputation for us. And when we look at the results from this model, we can see that they are closer to what we would expect from this population than either of the previous 2 strategies. So we like that. Now this here is the exact same data set. We use the same seed and the same code to generate it, so this bit up until here is exactly the same as the previous data set that we were looking at. But the probability of missingness is dependent on the value of y here. So we're using this thing here to get about 10% missingness across our data set. So in this case, we have data missing at random, but it's not completely at random. It appears from the model output here. I'm not showing all the code for it, but it's similar to what we ran above. It appears that from the model output that the coefficients didn't change that much. They're all fairly close to 1. The biggest difference that I notice here is that the predicted values we get from the model are a little lower, between the intercept being about 0.1 below 0 and the coefficient for G also being a little bit lower, our predicted values are going to be systematically lower than they should be, so they're biased. And this is a classical definition of bias. Our predicted values are systematically lower than they should be. The relationships are consistent with what we know about the system. So all these coefficients are, again, close to 1, as we expect. And it doesn't feel like much in this case. It's only a little bit lower, but the results are still biased. Overall, it's not terrible. But there may not, and there, when you get a data set in practice, there's probably not a really good way to measure how far off your model is. To measure that bias is going to be a very difficult challenge. Now, when we impute missing data, the net effect for the G=1 group is pretty much unchanged. So this rises a little bit, this drops a little bit. So that group, their estimates are going to still remain a little bit biased. But overall, this model doesn't look too bad. It's fine. Now, when we change the probability to be conditioned, again, we have the same data set, exact same data that we are generating. The only difference is we're throwing out a different subset of the data. So when we change the probability to be conditioned on both group 1 and Y, being in the top 50% of the distribution, so if we condition on G, and when Y is in the top half of the distribution, then we're at much greater risk of having missing data. Here we enter the realm of informative missingness. When we run our model, we can clearly see that the coefficient for G is much lower than it should be. And the confidence interval includes the value 0, which means we've lost statistical significance for that result as well. The rest of the coefficients seem to be fairly unchanged. Now here, when we impute the missing data, we end up with a model that looks very similar to what we should get. Again, based on how we simulated the data, all the coefficients except the intercept should be 1, and the coefficient for the intercept should be 0. So this is not, normally you wouldn't expect such a great outcome when imputing the data, but it worked out for this example. So we were able to recover the information that we had lost there because of our informative missingness by imputation. So in summary, be sure to think about missingness when you plan studies, and be extra sure to implement strategies to avoid informative missingness as much as you can. You shouldn't expect to be able to overcome the resulting bias, and you probably won't be able to measure the bias or even tell if it's there. When you do have a sizable amount of missing data, be sure to look at it carefully to identify possible biases and use imputation to recover some of your missing data. Thank you for watching.